Right, so we are going to begin chapter 3 today. So let's go ahead and start off with prayer. Dear Heavenly Father, Lord, thank you so much for today. Please be with us as we go over this content. Allow the information to be clear and understood. In Jesus' name I pray, amen. All right, so we are going to start off today with chapter 3. And also, we're going to, chapter 3 is combining with chapter 12, just the infrared spectroscopy area. So if you go to chapter 12, you'll see the sections there that we're going to be covering as well. So you should be reading chapter 3 and chapter 12 with this material. So let's go ahead and get started. All right, so in this lecture, we're going to be doing chapter 3.1, 12.5, and 12.6, where we're going to just do an introduction to spectroscopy. All right, so let's first talk about functional groups. So functional groups are the part of the molecule that give the properties and are responsible for the reactivity of the molecule. Now, different molecules can have multiple functional groups on it, and they would all act accordingly to whatever is in the mixture or the reaction at that time. All right, so functional groups affect the reactions, the structure, and the physical properties of every compound in which they occur in. Okay, so organic compounds can be grouped into families by their common structural features or their functional groups. And the groups react in a typical way, generally independent of the rest of the molecule. And so if you see here, and let me get my laser pointer, if you look at this structure here, you will see that in this structure, you have a double bond here. And this double bond is going to be a reaction site that's going to react in a certain way. Whereas here, this also has a double bond and it has a reaction site that's going to react in a certain way. Now, in this molecule, you also have a hydroxyl group, this OH group right here, which is also a type of functional group that we're going to talk about in the future. But let's look at the reactions of reactions, okay? So, for example, alkenes, whether they're simple or complex, they're going to react with bromine in the same way. So what would that look like? So here we have ethylene, and we see that when it reacts with bromine, you get two bromines on both sides of where the double bond was. And then now you have a more complex reaction of methane, okay? And this right here, if you notice that where the double bond is, it reacts with bromine the same way. So this is an example of how, whether the compound is simple or complex, if there's a double bond, typically is going to react in the same way or have similar reactivity. And so that's why we say in terms of functional groups, it's the function. It's the part of the compound that's going to have a certain physical, chemical feature, okay? Yes. So, well, another thing, I'll go ahead and tell you guys. So, for example, if I'm working with pharmaceutical company, if I'm looking for a drug that's going to do something, then what I would do is I would look at those functional groups, okay? If I'm trying to inhibit a certain enzyme, I'm going to look at what functional groups are going to interact with that and how can I change those functional groups to figure out what happens. And so this just shows you the importance of organic chemistry when it comes to biochemistry, molecular biology, or any of these things such as drug development. It's all about the functional groups. The functional groups can also help you predict what's potential side effects. How are they oriented? How do they fit in that Lockheed model? All right, so let's go ahead and we're going to take each of these functional groups and we're going to talk about some of these properties, what they're called, and kind of go from there. All right, so we're going to start with the simplest of simplest functional groups. And so an alkane, this is a carbon that doesn't have any double bonds on them. We call those alkanes. Alkanes, we typically say, are not functional groups, okay? They're just the base structure of organic compounds. However, once you become an alkene, which means it has a double bond, okay? So when you have double bonds, as you see down here, when you have double bonds, those are referred to as alkenes, okay? That A is turned into an E. So from an alkane, you now become an alkene. And then if you have a triple bond, that's called an alkyne. Okay, that A became a Y, an alkyne. And this is when you have a triple bond. Now, when you have a cyclic six-membered ring, and if you notice, it's double bond, single bond, double bond, single bond, double bond, single bonds in a cyclic way. Okay, we call that conjugated. That's called an arene or an aromatic ring, okay? So that's an arene, aka an aromatic ring. So whenever you hear someone say an aromatic ring or an arene, they're referring to that member ring that has the conjugation, a pattern of double bond, single bond, double bond, single bond, double bond, single bond, around and around. All right, so as you see, we see the first three that we talked about, the alkene, the alkyne, the arene. And you can see in terms of how the names are ended. So when compounds end with the ene, that's an alkene. YNE is alkyne. Aromatic rings, they don't have endings. They're considered substituents, or they just are, and we'll talk about that a little bit later. So they don't really have anything like that. Halides don't have name endings either. Halides are when you're attaching a halogen. Okay, so a halide could be a bromide, it could be a chloride, an iodide, a fluoride. Okay, those are all, or you can say chloro and whatever it is. And again, we'll talk about the naming a little bit later. But when you see halogens, those are called halides. Okay, so if I say identify, that's a halide. All right. Or you can be specific and say bromide, iodide, fluoride. That's both acceptable. Next, you have OH groups. Okay. Those are referred to as alcohols. So when you have an OH group attached to a organic structure, that's considered an alcohol. And the ending of alcohols is OL. Next, we have ethers. So when you have an oxygen and then two carbons that are single bonded to it, that is called an ether, okay? So, and then as I'm going through these, I want you guys just to make notes. If you need to do flashcards, that's also something that's very beneficial and recommended. All right, so next we have, and again, we're going through these really fast, and then I'll be breaking up the main ones that we use in organic chemistry. So next we have a monophosphate. And that's when you have one phosphate group. Okay, that's a monophosphate. I'm sure you guys have seen those in biology class if you've taken that. If you have two phosphates, that's a diphosphate. Okay, and the phosphate group is the part that's red, or excuse me, that's pink. Okay, that is a phosphate group, diphosphate group. Next functional group we have is an amine. So whenever you see something that ends with an amine, when you have like methylamine, ethylamine, those are amine groups. And amine groups, and again, we'll talk about, we have primary, secondary, tertiary amines. We'll talk about that later on. But amine group is when you have a carbon single bond to a nitrogen, and those nitrogens can have other things attached to it, whether it's hydrogens or other carbons as well. Now, an imine is when carbon is double bonded to the nitrogen. Okay, that's an imine. So you have amine when it's one. So you have a bond of amine. And then imine is when you have two double bonds. I try to figure out ways to remember these. I always say I'm double amine. You know, I'm super mean, double amine. All right, so imines are very mean, you know, so they're double. I don't know. All right, so then you have a nitrile group. Nitrile group is when carbon is triple bonded to that nitrogen. These are popular in organic chemistry as well. You'll see them in second semester. Next, you have thiol, which you have a carbon single bond to a sulfur with a hydrogen attached to that sulfur, okay? So you have thiols. Thiols are really popular in biological compounds, as well as sulfides. I'm sure you guys have seen sulfide bonds, right? In molecular biology or biochemistry. So you have sulfide bonds. That's that's when the sulfur is in between two carbons. It's similar to how we have ethers. Okay, we know that sulfur and oxygen are in the same group, right? On the periodic table. So you have an oxygen in between the two, you have an ether. If you have a sulfur in between the two, you have a sulfide. Okay, and they have some similar properties. Disulfide is when you have two sulfur groups. Now, oxygen does have a counter one that's like that. We call those peroxides. I don't believe it's in this list. I have to say I can't remember, but you do have that. You have sulfoxides. You hear that oxide, sulfoxide. So you hear that oxide, you're referring to an oxygen, right? So it's a sulfur oxide, sulfoxide. And so with that, you have your sulfur that's connected to carbon. And then you have your oxygen off of that, okay? A sulfoxide. Next, you have we're going to have our carbonyl ones. These are all ones that have carbonyl groups. So you see this carbon with a double bond O, that's called a carbonyl group. And when a carbonyl group is attached to a carbon, has attached to at least one hydrogen, you have that called an aldehyde, okay, aldehyde. When the carbonyl group has two carbons on both sides and there's no hydrogens at all next to the carbonyl group, that's called a ketone. Ketone. Now, keep going on. You have a carbonyl group, and this time, if you have an OH attached to at least one side of the carbonyl group, you call that a carboxylic acid. And so those are your acids, like you see acetic acid, malic acid, those are lactic acid, those are all carboxylic acids. All right, so what happens when you no longer have a carboxylic acid? That hydrogen is replaced with a carbon. We call those esters, okay? Esters. And we know they're esters when they end with O8. All right, so methyl ethanoate. All right, that's an ester when you hear OATE at the end. Next, you have a thioester. Okay, in this case, you have a sulfur instead of an oxygen. So that thio again. All right. Keep coming down. You have amides. All right, so amide is like an amine, but it's connected to a carbonyl group. So you have an amine, and then when you add a carbonyl group, that's an amide. Okay, amide. Next, you have acid chlorides. All right, acid chloride is when you have a carbonyl group and then a chlorine attached to it. And then you have a carboxylic acid anhydride, or you can say acid anhydride. When you have an acid anhydride, that's when you have two carbonyl groups and then an oxygen connecting them in the middle. And again, we're going through these quickly, but the ones that are important, we're going to focus on a little bit more. All right, so now it's time to kind of go and dig deeper in these functional groups. All right, so these are functional groups where a carbon is single bonded to an electronegative atom. So these are alkyl halides, also known haloalkanes. These are alcohols, these are ethers, these are alkyl sulfates, amines, thiols, sulfides, disulfides. They all have a carbon that's single bonded to an electronegative atom. So these bonds between the carbon and electronegative atom are polar covalent bonds, okay? These are polar covalent bonds. So let's look at them again, okay? If you notice when you're looking at it and you're seeing the electronegative map, all right, you see that there's polarity in all of these. But you're looking at how strong is this polarity based on the colors. You can kind of see that. So with this one, it's an alkyl halide again. You have alcohols, and notice they're all single bonded to carbons. This is your ether. This is your phosphate group. Very electronegative. This is your amine. Okay. Here you have your thiol, sulfide, and your disulfide bond. Okay. Now, you have your next classification, which is your carbon-oxygen double bonded. These are your carbonyl group ones that we just talked about. We're going to just look at them again. So carbonyl groups are present in a large majority of organic compounds and biological molecules. You're going to see carbonyl groups over and over again. Even after this class, you're going to see these carbonyl groups. Now, in this class, in part 2, because it's towards the end, sometimes we don't get to study it as much, but I empower you guys to kind of look at the patterns so that you're able to see and recognize these carbonyl groups and the functionality of these carbonyl groups. So all of these compounds in this classification, they behave similar in many aspects. Now, there's differences, but they do behave very similar often, okay? Now, they differ depending on the identity of the atom bonded to the carbonyl group carbon. All right, so while the carbonyl group may have similar properties, because it was bonded to the carbonyl, that does give its individuality. And so again, looking at them all together, you have your aldehyde, your ketone, your carboxylic acid, your ester, your thioester, your amide, and your acid chloride, okay? They don't have the acid anhydride on here, but these are your big heavy hitters, okay? Especially the top ones, the top 4, and then your amide and your acid chloride. The thioester in this class, we don't talk about it a whole lot, but just be mindful of it. All right, so who are your main players in organic chemistry for this level? These are your main players. Now, the other ones are very important, but if you had to only have so much space in your mind to memorize them, to at least have at least 80 to 90% of the information that you need, these are going to be your heavy hitters, your alkenes, your alkynes. I have alkanes on there just because your benzene rings. So these are all your hydrocarbons at the top. Then you have your single bonded oxygen ones, your amines, your alcohols, your ethers, your alkyl halides, and your thiols. Important, okay? And then your aldehyde, the carbonyl ones that you guys want to make sure you do. Aldehydes, ketones, esters, carboxylic acids, and amides. If you don't know anything else, you need to know these right here. All right, so let's do this example. It says, identify the functional groups the molecules have in methane 9. Okay, so we're going to look for these functional groups here. So I'm going to pull out my pen, and I am going to walk you guys through this first one. So first, you're going to notice that you have this group here. You have this group here. And then you have this lovely guy here in the middle. Okay. So you have a sulfur that's in the middle. You have a functional group that's I have highlighted in the red. So if you guys know what that is, I want you guys to take a guess. I know we just ran through those, but I don't know if you guys remember any of those from before. Matter of fact, if you take biochemistry, you should be able to recognize this as being an amino acid, a type of amino acid, because it has an amine and a carboxylic acid on it. But let's go ahead and go through that. So you have your sulfide, because the sulfur is right there in the middle. Your carboxylic acid here. And then your amine, it's going to be right there. Okay. And so this is kind of how you identify your functional groups. So you would just look at where everything is and then try to identify what those are. Okay, but even if you don't know the names of them, if at least you can recognize them as functional groups, you're halfway there. All right, let's see if you guys, let's keep going. All right, so identify the functional groups in the following compounds. So let's see if we can at least identify some of these. All right, we have a functional group here. We have a functional group here. Now, with this one, I didn't talk about it, but we will talk about that one next class. So I'm going to break it up into two for today. Right. So with the first one, you have your ester, not to get mistaken for as your carboxylic acid, because it has a carbon on the other side, not an OH group, that's an ester. Then we have our alcohol. And then last we have our benzene, or you can call it an arene. Now, why did I color the purple? Well, the reason why I have the purple there is because whenever you have an alcohol or an OH group attached to a benzene ring, we actually refer to that because it has its own functionality as a phenol. Okay, so you don't have to break it up and say an alcohol and a benzene. It becomes one functionality, which is phenol. Okay, that one functionality that is phenol. And so that's why I highlighted it all together. So you really have a phenol and an ester right there. All right. And methyl salicylate is actually a starting material for something that is very common. All right. And we'll talk about that a little bit later. All right. So next you have salicylic acid, which you notice is very similar to that methyl salicylate. So let's see if you guys can tell me what the functional groups of that one is. Let's first start off with what I'm highlighting as purple. What is that functional group? And then also, what is the functional group of what I'm highlighting in red? We just talked about this one. Awesome. All right, so the functional group in the purple is what we call, and let me erase our last one. Is called a carboxylic acid. And if you remember, what I highlighted in red is referred to as a phenol. Excellent. All right. See, not too bad. All right. So next, let's see what we have here. This is aspirin. And this is what I was talking about in terms of the starting material. So aspirin is, well, methyl salicylate actually is a starting material, and we can do esterification to actually get winter fresh. While salicylic acid, you can start that as a starting material to actually do aspirin. And the reaction is called esterification because what it does is it makes an ester. So let's look at this. And I kind of gave you guys a hint, right? I said ester, right? So what is the functional group of this right here? Okay, what is that functional group? And then what is the functional group of this right here? And then last, what is the functional group of this right here? All right, so if we're looking at this, the functional group of the first one would be an ester. All right, so we're just repetition is good. And then again, we have another carboxylic acid. And then last, you guys should know that's an arene, or referred to as a benzene. Very good. All right, let's keep going. Let's do a little more practice. All right, so we have some other functional groups in here. We have acetaminophen. Have you guys heard of acetaminophen before? I'm sure you possibly have. Acetaminophen is actually Tylenol, is the active ingredient in Tylenol. And so let's see what functional groups we have here. So let's see. We first have a functional group here. Okay. And then we have another functional group here. So what is that functional group? Well, the functional group that we have in purple is phenol. Again, we have that OH attached to that benzene ring. And then the next functional group that we have here is an amide. Remember, amides have that carbonyl group with that nitrogen attached to it. That's an amide. All right, so let's look at this next one. So we have this oxygen single bonded to a carbon there. All right. And so that one is referred to as our ether. Again, ether is when you have an oxygen with two carbons on both sides. That's an ether. And those carbons can be attached to anything else. It doesn't matter what it's attached to. As long as you have an oxygen single bondedly to two carbons, that's referred to, and I spelled that ether wrong, I apologize. That's referred to as an ether. All right, ether. Now there's another functional group inside of this compound. Can you tell me what that is? All right, so you should have been able to identify this right here. And that's going to be an amide. All right, very good. All right, let us go to the next one. All right, so on this next one, we have a functional group here. And then there's a functional group here. Well, let me do a different color. All right, so with these functional groups, again, you have an arene. Now notice, don't get confused. Even though there's an OH in the arene, the OH is not directly attached to the arene, so that would not be a phenol, okay? It's not directly attached to it. So that is going to actually be an alcohol. For it to be a phenol, it has to be directly attached to the ring. Okay? Now for the next one. What functional group do you see on there? All right, let's see if you guys got it right. With the next one, we have a functional group here. Now notice, it's an OH group that's attached to a ring, but is that ring a benzene ring? No, it's not. And so that is not a phenol, but simply a regular alcohol. So make sure when you're doing them, when you make sure you don't get them mixed up. Phenols have to be attached to a aromatic ring. If it's not, it's simply a regular alcohol. And even though there's other things attached to this ring, those are all single bonds. So there's nothing on there that's telling me there's a functional group there. All right, you guys, so that is all of those. All right, so we're going to now move into the next part. We're going into 12.5 when we're talking about infrared spectroscopy, IR spectroscopy. So to talk about IR spectroscopy, let's first talk about what the electromagnetic radiation is, okay? So electromagnetic radiation, or the electromagnetic spectrum, I'm sure you guys have heard before time and time again, it is the light spectrum, right? And so with the light spectrum, or with magnetic radiation, it's going to possess the properties of a photon, but behave as an energy wave, okay? So it possesses the properties of a photon, but it behaves as an energy wave, so it has wave functionality. So why is this important in reference to organic chemistry? Well, organic compounds exposed to electromagnetic radiation can absorb energy of only certain wavelengths, units of energy. All right, so organic compounds absorb the energy, and not just any energy or every energy, specific energy based on certain properties. So the changing in wavelengths to determine which are absorbed and which are transmitted produces an absorption spectrum. So when, depending on which wavelength is absorbed, you can create an absorption spectrum, okay, or spectra, okay? And so you can create a graph, if you will. And specifically infrared radiation, these absorbs energy, causes bonds to stretch and bend more vigorously. And so bonds are already kind of moving and stretching and flexing, but when they're hit with this infrared light, they stretch and they bend even more than normal. Now, we also have ultraviolet radiation, and these absorb energy, causes electrons to jump to a higher energy orbital. Now, we're not going to talk about ultraviolet in this lesson, but later on we will. So the infrared region that you see here is right below the visible light. All right, so you have visible light here. And you see the infrared is just below that. And it's just above microwaves. All right. And so when you're looking at this, you're going to take note of what's going to happen. So it's just enough waves or just enough energy for your bonds to vibrate, but electrons aren't moving and jumping to other lengths. So, with infrared energy modes, molecules possess a certain amount of energy that causes them to vibrate. And so, what that means is that when the frequency of the electromagnetic radiation matches the frequency of the molecules, they actually vibrate. And so it's kind of like a tuning fork, if you will. If anybody who's ever used a tuning fork or know how to use a tuning fork, what happens is you have a tuning fork, and when the note is played and the tuning fork vibrates, when those frequencies are the same, when the notes are the same. So it's kind of similar to that. And so molecules absorbs energy upon electromagnetic radiation only if the radiation frequency and the vibration frequency matches. Okay, so when they match, this energy is absorbed into the molecules. Now, when they absorb, they could do a couple of things. So let's imagine that you have the bonds. Okay, you have these bonds. And so let's say that this right here is let's say it's just a nitrogen or anything, right? A carbon. And these right here are the atoms that are connected to this center atom. And so bonds can either stretch, and so the bond lengths are actually stretching, kind of like a spring. So if you had a spring and you pull the spring, they're stretching, okay? And they can stretch symmetrically. So that means both of them are stretching together in and out. Or they can stretch asymmetrically. So where one goes and the other one's going out. So it's kind of stretching like this. Okay, but again, it's the bond lengths. Now, in addition to stretching, bonds can also bend. And so if you have your, again, your angle, if the bond is going in plane and they're both coming towards each other, then outward of each other, that is called scissoring. So when the bond stretches like, bends like this, it's called stretching. When they're moving in the same direction and bending, that's called rocking. So they're both going right together and they're both going left together. Okay, so the right and left are together. Now, when they're moving out of plane and they're both going, well, let's say one is going away from you and one is going towards you, that's called twisting. So they're kind of like twisting out of plane like this. Okay. So they're kind of twisting. When they're both going together, away and towards you, that's called wagging. All right. And so these are the different energy modes that can happen. So you can have stretching and you can have bending. Now, an atom can stretch and bend at the same time as well. And they kind of can be doing different things at the same time, or stretching while they're scissoring. So it's kind of like scissoring, stretching, and so all that kind of stuff. So you can do them at the same time. But these absorptions, or I should say these modes absorb in certain areas based on the electromagnetic, or certain areas, or at certain wavelengths based on the matching frequencies. All right, so just to kind of reiterate this, so when the frequency of the IR light equals the frequency of the bond stretching, IR light is absorbed. Okay, so again, when they match, that's when the light is absorbed. So why is this important? It's important because the different kinds of bonds vibrate at different frequencies. So they absorb different frequencies of IR light. So since the frequencies of these bonds are different, they absorb at different lights. And so if I measure at what frequency the bonds are absorbing, I can use that information to distinguish the different types of bonds in a molecule. Okay, so if I'm shining a light and I'm using an instrument or a machine to say, okay, at what point is this light being absorbed, I can record that, display it, and watch it, look at it to determine, because again, remember, different bonds absorb at different frequencies. So let's say that if a carbon-hydrogen bond absorbs light at A frequency, okay, let's say it's A. I'm just using A. We'll talk about actual numbers, but let's say it's at A. All right. If I shine light on it and I shine it at B, C, D, nothing's going to happen. But as soon as I shine it at A and I see that absorbance, I know, okay, there's a carbon-hydrogen bond in there because it matched, it absorbed. And so you can use that as a differentiating mechanism or mechanics, okay? And when you have these different, remember, functional groups are based on different things being connected in a combination. So if I look at the different types of bonds being absorbed, I can use that to determine the functional groups present. Because if I see a carbon single bonded to an oxygen absorption bands, I know that that could be an alcohol, it can be an ether, it could be an ester, it's something that needs a carbon oxygen. So then I'm looking at different absorbances. I can use all the information to determine the functional groups. Now, I may not know how they're connected to each other, but I can tell the different types of bonds. Therefore, I can tell the different types of functional groups present in a molecule. And so that is the end in terms of the introduction. So the takeaway from the IR part, know that bonds absorb at a certain frequency. And when those frequencies match, as you're shining the light on them, you're able to see that absorbance. And using that information, you can determine the different types of frequencies. So that is all for today. And we're going to continue this conversation with the next lecture in the next module. So I will, until then, we'll see each other again.